There is a moment burned into the memory of every person alive who was old enough to witness it. July 20th, 1969. A human being stepped off a ladder and onto the surface of another world for the very first time in history. The entire planet watched. And then it happened again, and again, and again. 6 times in total, 12 men walked on the moon between 1969 and 1972. And then, just like that, it stopped. No one went back. Not in the 1980s, not in the 1990s, not in the 2000s, not in the 2010s. For over 5 decades, the moon sat there in the sky, close enough to see with your naked eye, close enough to drive to if you could somehow point your car straight up and keep going for about 4 months, and yet no human being returned to its surface. If you find that strange, you are not alone, because when you sit down and actually think about it, it makes almost no sense at all. We had the technology, we had the rockets, we had the trained astronauts, we had the agencies and the budgets and the knowledge. And yet, for 54 years, humanity just looked at the moon and did nothing. The official explanations have always been money, budget cuts, political will, shifting priorities. And those things are real. Those things did happen. But they are not the whole story, not even close. Because underneath the clean, simple narrative that gets repeated in history books and documentaries, there is something far more complicated. A web of decisions and miscalculations and hidden fears and engineering nightmares and political disasters that together explain why going back to the moon turned out to be almost impossibly hard. And if you stick with this to the end, you are going to walk away with a completely different understanding of one of the most fascinating and honestly kind of troubling stories in human history. The real reason we stopped going to the moon is not what you think. And the real reason it took 54 years to go back is even more surprising. So let's start at the beginning. Because to understand why we stopped, you first have to understand exactly what it took to get there in the first place. If you are enjoying this kind of deep dive into the real stories behind space exploration, do us a favor right now and hit that subscribe button. There is a lot more where this came from, and you do not want to miss it. So, 1961. The world is in the middle of the Cold War. The Soviet Union and the United States are locked in a competition that goes far beyond military hardware and nuclear weapons. It is a battle of ideology and prestige, and the ultimate demonstration of which system, capitalism or communism, is superior. And the arena for that battle has moved to space. The Soviets drew first blood in 1957 when they launched Sputnik, the world's first artificial satellite. A tiny metal sphere the size of a beach ball that beeped as it orbited the Earth and sent the American political establishment into a full panic. Then in 1961, they did something even more astonishing. They sent a man to space. Yuri Gagarin became the first human being to leave the Earth and return safely, and the propaganda value for the Soviet Union was incalculable. The message was clear. Communism can do what capitalism cannot. President John F. Kennedy needed a response, and he chose the most audacious, most impossible-sounding response available. He stood before Congress and declared that the United States would put a man on the moon before the end of the decade, not in some vague, distant future. By 1969, in less than 9 years. Keep in mind that at the time Kennedy made this speech, the total amount of time American astronauts had spent in space was exactly 15 minutes. 15 minutes. The longest spaceflight ever attempted at that point was Alan Shepard's suborbital hop, and it barely qualified as going to space at all. But Kennedy committed to it anyway, and NASA, which had only existed for 3 years at the time, got an almost unlimited budget and an impossible deadline, and was told to figure it out. What followed was one of the most extraordinary engineering efforts in human history. At its peak, the Apollo program employed around 400,000 people, engineers, scientists, mathematicians, welders, seamstresses, electricians, and programmers, all working toward a single goal. The budget at its height consumed roughly 4% of the entire federal budget of the United States. To put that in modern terms, that would be somewhere in the neighborhood of $200 billion a year today. And they did it. On July 20th, 1969, Neil Armstrong and Buzz Aldrin landed on the moon, while Michael Collins orbited above. Armstrong stepped off the lunar module and said those famous words, and every television set on Earth carried the image. It was genuinely one of the greatest moments in human history. But here is what the celebrations at Mission Control did not tell you. Here is what the champagne and the parades and the ticker tape did not reveal. Behind the triumph, NASA was already in trouble. Deep, serious, existential trouble. And the seeds of the 54-year gap were planted even before the first moon landing happened. The problem was fundamentally this. Apollo was a crisis program. It was born out of a geopolitical emergency, funded like an emergency, and staffed like an emergency. The entire infrastructure of the program, every rocket, every launch pad, every control system, every spacesuit, was designed for one specific purpose. Get to the moon before the Soviets, not to establish a permanent presence, not to build a sustainable framework for ongoing exploration, just to win. And once you win, the emergency is over. And once the emergency is over, the money starts to disappear. By the time Armstrong walked on the moon, NASA's budget had already started to decline. The peak was actually 1966, 3 years before the first landing. The political will that had sustained the massive investment was already eroding. Because here is the uncomfortable truth about the space race. It was never really about the moon. The moon was a trophy. The race was about proving American technological and political superiority. And once that was proven, the reason to keep spending money at that level became very hard to justify. Apollo 11 landed. The trophy was won. And the question immediately became, what exactly are we spending all this money for now? Congress started asking that question in 1969. They were still asking it in 1970. And by 1972, they had their answer. Not much. And they cut the funding accordingly. Now here is where things get really interesting. Because the story of why we did not go back to the moon is actually the story of several decisions that seemed reasonable at the time and turned out to be catastrophically wrong. And the first and most important of those decisions was the decision about what to build after Apollo. In the early 1970s, NASA had grand plans. They were not thinking small. The vision that Wernher von Braun and other NASA planners had laid out was breathtaking in its ambition. The idea was that Apollo was just the beginning. The next step would be a massive space station in low Earth orbit, a permanently crewed facility that would serve as a staging point for further exploration. After that, a reusable space shuttle that would make getting to and from that station routine and affordable. After that, a lunar base, a permanent human outpost on the moon. And after that, Mars. It was a logical progression. Each step built on the last, each step made the next one easier, and on paper, it made perfect sense. But Congress and the Nixon administration did not approve the whole plan. They approved part of it. Specifically, they approved the space shuttle, and they approved it under conditions that changed its design in ways that would haunt NASA for decades. The original space shuttle concept was a fully reusable two-stage vehicle. Both the orbiter and the booster would return to Earth and land like airplanes, be refueled, and fly again. It was designed to make spaceflight as routine and as cheap as possible. If it worked as designed, it could theoretically have made getting to orbit as straightforward as getting on a commercial flight, or at least dramatically less expensive than anything that had come before. But to get the funding approved, NASA had to make a deal. The Department of Defense wanted to use the shuttle for their own satellite launches, and to accommodate the military's requirements, the design had to change. The orbiter needed to be bigger, the launch profile needed to be different, and to keep costs down during development, the design shifted from fully reusable to partially reusable. The solid rocket boosters could be recovered and refueled, but the giant external fuel tank, the enormous orange cylinder you always see in the launch photos, was expendable. It would burn up on re-entry. These compromises did not seem like deal breakers at the time, but they fundamentally changed the economics of the vehicle, and those changed economics had a knock-on effect that rippled through everything NASA tried to do for the next 40 years. The shuttle was sold to Congress and the American public on a specific promise. It would fly frequently. Up to 50 flights per year was the initial optimistic projection, which eventually settled down to a more realistic, but still ambitious target of around 24 flights per year, and those frequent flights would dramatically reduce the cost of getting payload to orbit. The shuttle was supposed to pay for itself by making access to space cheap and routine. It did not work out that way. The shuttle turned out to be extraordinarily expensive to maintain. The thermal protection system, the thousands of heat-resistant tiles that covered the orbiter's surface to protect it from the searing temperatures of re-entry, required constant inspection and frequent replacement. Each tile was handmade and unique. You could not just order a box of them. After every flight, technicians went over the entire vehicle by hand, tile by tile, checking each one individually. That process took months. The shuttle ended up flying not 24 times a year, but somewhere around 4 to 5 times a year on average over the course of its history. And the cost per flight, instead of dropping as the program scaled up, remained stubbornly enormous. Each shuttle mission ended up costing somewhere around $1.5 billion. Some estimates put it even higher. The shuttle was not cheap access to space. It was the most expensive access to space that had ever been built. And here is where the really painful irony comes in. Because while NASA was sinking its entire human spaceflight budget into this one system, the system that was supposed to enable everything else, the Moon, Mars, the Grand Vision, the shuttle was actually consuming all the oxygen in the room. There was no budget left for anything beyond the shuttle itself. The space station got built eventually, in the form of the International Space Station, but it took until the late 1990s to even begin construction and was not completed until 2011, by which point the shuttle program was ending. The lunar base never happened. Mars never happened. The grand progression of von Braun's vision got stuck at step 1 and never moved. Now let's talk about the Moon specifically. Because beyond the budget problems and the shuttle issues, there was something else going on. Something that does not get talked about nearly enough. And that is the question of what exactly NASA was supposed to do on the Moon once they got there. The 6 Apollo landings brought back around 842 pounds of lunar rocks and soil. The astronauts took photographs. They set up seismometers and other scientific instruments. They drove around in the lunar rover. And by the time Apollo 17 landed in December 1972, scientists had learned an enormous amount about the Moon's geology and history and formation. In scientific terms, the Apollo missions were a staggering success. But in terms of public excitement, there was a problem. After Apollo 11, the Moon landings stopped being front-page news. The American public, famously prone to short attention spans when it comes to spectacular achievements, had already moved on. Apollo 12 got decent coverage. Apollo 13, the famous near disaster, gripped the world in a way that the successful missions almost could not. But by Apollo 14 and beyond, the television networks were no longer even airing the moonwalks in prime time. The ratings were not there. This sounds almost unbelievably cynical, and it is. But it is also real. NASA was trying to justify an enormous budget to a Congress that answered to voters who were no longer watching, and without a clear, compelling, ongoing reason to keep sending people to the Moon, the argument for continued funding kept losing ground. There were proposals. NASA put forward concepts for extended Apollo missions, for a lunar orbital station, for robotic prospectors that would scout landing sites for future crewed missions. But each proposal required money that was no longer available, and the political will to spend that money had evaporated along with the public's attention. Apollo 17 landed in December 1972. Apollo 18, 19, and 20 had already been canceled. The hardware existed. The rockets were built. The flight plans were drawn up. But the missions were canceled anyway, because the money was gone, and the will to fight for it had gone with it. And then for 5 decades, silence. But here is the thing that makes this story so much more than just a tale of budget cuts and political failures. Because even as human beings stopped going to the Moon itself kept revealing new secrets. Secrets that would eventually transform it from a visited trophy into something far more valuable. And understanding those secrets is essential to understanding why the world, 54 years later, suddenly decided it was time to go back. Let's talk about water, because water changes everything. For decades after the Apollo missions, the scientific consensus on the Moon was that it was completely and utterly dry. a bone-dry, airless, geologically dead rock. The Apollo samples confirmed that the surface rocks contained almost no water at all, and the assumption was that this was true of the entire moon. The intense solar radiation and the lack of any protective atmosphere meant that any water molecules on the surface would be quickly broken apart by ultraviolet light. This assumption was enormously consequential, because a dry moon is a moon that is extraordinarily hard to sustain any kind of long-term human presence on. You cannot drink it, you cannot grow food with it, you cannot split it into hydrogen and oxygen for rocket fuel. You have to bring everything with you, and bringing everything with you from Earth is almost impossibly expensive. But then, in the 1990s, something started to change. Radar observations from spacecraft suggested that there might be ice lurking in the permanently shadowed craters near the lunar poles. The logic was elegant. The moon is tilted only about 1.5 degrees relative to its orbit around the sun. This means that at the lunar poles, some craters are so deep and so oriented that sunlight never reaches their floors. Not once. For billions of years, these crater floors have sat in absolute darkness at temperatures that can drop to around -250 degrees Celsius, cold enough to trap and preserve water ice that might have been deposited there by impacting comets and asteroids over billions of years. The evidence was suggestive but not definitive, until 2009. In October 2009, NASA deliberately crashed a rocket stage into a permanently shadowed crater near the moon's south pole. The mission was called LCROSS, the Lunar Crater Observation and Sensing Satellite. The plan was to observe the plume of debris kicked up by the impact and analyze it for signs of water. And when the data came back, it was unambiguous. Water, ice, lots of it, buried in the lunar soil inside that permanently shadowed crater. Subsequent missions filled in more of the picture. China's lunar orbiters, India's Chandrayaan missions, NASA's Lunar Reconnaissance Orbiter, all built on each other to paint an increasingly detailed map of the lunar water distribution. And what emerged was extraordinary. There are enormous reserves of water ice at both lunar poles, concentrated in the permanently shadowed regions, but apparently more widespread than anyone had initially imagined. The most recent estimates suggest that there could be hundreds of millions, possibly even billions of metric tons of water ice on the moon. That number is not certain. The distribution is patchy, and the depths are unknown. But the existence of substantial water ice is now essentially settled science. And this changes the moon from a visited trophy into a resource, a starting point, a way station. The water can be used for drinking, for agriculture in pressurized habitats, and most critically, it can be split by electrolysis, using solar power, into its component parts, hydrogen and oxygen, which happen to be the two best rocket propellants we know of. The moon, it turns out, might be a gas station, a refueling depot at the edge of the Earth's gravity well, where spacecraft heading out into the solar system could top off their tanks without having to haul everything up from the bottom of Earth's enormous gravity well. Because here is a piece of physics that shapes everything about space exploration. Earth's gravity is deep, really deep. Getting a kilogram of anything off the surface of the Earth and into orbit takes roughly 10 kilograms of propellant. The ratio is brutal. Most of a rocket's launch mass is fuel just to lift more fuel. The moon's gravity is only about 1/6 of Earth's. Launching from the moon requires dramatically less propellant. If you can make propellant on the moon from local water ice, the economics of deep space exploration change completely. Instead of launching everything from Earth, you launch the equipment and the people, you manufacture the fuel on the moon, and you leave for Mars or the asteroids or anywhere else from there. This is not science fiction. This is physics and chemistry, and it means that the moon is not a destination. It is an infrastructure project, a critical piece of the architecture of everything that comes after. That realization took time to fully sink in, but by the 2000s and especially the 2010s, it had become increasingly central to how NASA and space planners around the world were thinking about the future. But there is something else going on at the same time that is just as important, and it is something that almost nobody talks about when they discuss the return to the moon. And that is what happened to the price of getting to space. For the entire history of the space shuttle era, the cost of launching payload to orbit was stuck in an incredibly expensive range. roughly $10,000 to $20,000 per kilogram to low Earth orbit. At those prices, building large structures in space, building a lunar base, sending large amounts of equipment anywhere beyond low Earth orbit was almost unthinkably expensive. And then SpaceX happened. The story of what Elon Musk's rocket company did to the launch industry is genuinely one of the most significant developments in the history of space exploration. And the key innovation was something that seemed almost impossibly ambitious when it was first proposed: landing and reusing orbital rocket boosters. Every rocket before SpaceX's Falcon 9 was expendable. You launch it, you use it, you throw it away. The entire first stage, which is the most expensive part of the rocket, falls into the ocean after separation and is never seen again. SpaceX looked at this and asked a question that sounds obvious once you hear it, but that the entire industry had essentially given up on. What if you landed the booster and flew it again? The first time SpaceX successfully landed a Falcon 9 first stage, in December 2015, it was genuinely stunning. A rocket stage that had just launched a payload into orbit came back down and landed on its own legs, engines firing, soft as a feather. People in the crowd were crying. Veteran aerospace engineers who had spent careers working on expendable rockets watched the footage with expressions somewhere between amazement and disbelief. And then SpaceX did it again, and eventually they were routinely landing the same booster over and over, flying the same first stage more than a dozen times. The cost of launching payload to orbit started to drop dramatically. The Falcon 9 brought the cost down to somewhere around $2,000 to $3,000 per kilogram to low Earth orbit. And SpaceX's next-generation rocket, Starship, which is a fully reusable two-stage vehicle of absolutely enormous size, is designed to bring that number down even further, potentially to the hundreds of dollars per kilogram range if it works as planned. This matters enormously for the return to the moon, because when launch costs are high, almost everything is off the table. When launch costs drop significantly, the range of what is economically possible expands dramatically. But even this is not the complete picture, because the return to the moon is not just a NASA story. Not anymore. And this is where things get really interesting and, honestly, a little bit concerning. Let's talk about who else is going to the moon. Because the space race of the 21st century looks very different from the one that played out in the 1960s. China has a space program that has been executing with remarkable precision and ambition for the past 2 decades. In 2003, they became only the 3rd country to independently send a human to orbit. In 2013, they landed a rover on the moon. In 2019, they did something no one had ever done before. They landed a spacecraft on the far side of the moon. The far side is the hemisphere that never faces Earth, which means you cannot communicate with a spacecraft there directly. China solved this problem by placing a relay satellite at a gravitationally stable point beyond the moon to maintain communications with the lander. It was a genuine technical achievement. And in 2020, they returned lunar samples to Earth for the first time since the Soviet Union did it in 1976. Not with a crewed mission, but with a sophisticated robotic sample return mission. The samples came from a region of the moon that had never been sampled before. China's stated plans include landing Chinese astronauts on the moon, establishing a robotic research station at the lunar South Pole, and eventually building a permanent crewed lunar base. The timeline they have publicly committed to puts crewed lunar landings in the early to mid-2030s. The International Lunar Research Station, as they are calling their base project, is being developed in partnership with Russia and is open to participation from other countries that want to join on China's terms. Now, the lunar South Pole is not a random choice. The lunar South Pole is where the water ice is, where the permanently shadowed craters are, where the resources are, and there is only so much of the most valuable terrain to go around. This is not lost on American policymakers, and it is not a coincidence that the primary target for NASA's Artemis program, the initiative designed to return American astronauts to the moon, is also the lunar South Pole. The Artemis program was announced in 2017 under the Trump administration, with a target of returning American astronauts to the moon by 2024. That deadline has slipped significantly, as rocket program deadlines almost inevitably do. But the program is real, it is funded, and it represents the most serious, sustained American commitment to returning to the moon since the end of Apollo. And the architecture of Artemis is fundamentally different from Apollo in ways that reveal how much has changed. Apollo was a flags and footprints mission. Get there, do science, come home, prove the point. Artemis is explicitly designed to establish a sustained human presence, not just to visit, but to stay. The cornerstone of the Artemis architecture is a small space station in lunar orbit, called the Gateway. Unlike the International Space Station, which orbits Earth, the Gateway would orbit the Moon, serving as a staging point for lunar surface missions. Astronauts would travel from Earth to the Gateway, then descend to the surface from there, then return to the Gateway before heading home. This architecture allows for more flexible access to different parts of the lunar surface, and provides a permanent outpost in the lunar vicinity even when no one is on the surface. The Surface Landing System for Artemis, the vehicle that would actually take astronauts from lunar orbit down to the surface, is being developed by SpaceX. Specifically, it is a version of the Starship vehicle adapted for lunar landing, which is a genuinely enormous spacecraft, much larger than the lunar module that carried Apollo astronauts to the surface. But the Artemis program has not been smooth. The Space Launch System, NASA's new heavy lift rocket that is central to the program, has been in development since 2011 and has cost somewhere in the region of $23 billion so far, with critics arguing that it costs so much per launch that it is economically unsustainable for the kind of frequent moon missions that Artemis envisions. The SLS first launched in November 2022, over a year behind schedule, on the uncrewed Artemis 1 mission that sent an Orion capsule around the moon and back. The mission worked. The capsule splashed down in the Pacific and was recovered successfully. The crewed version of that mission, Artemis 2, would carry astronauts on a flight around the moon without landing. Artemis 3 is planned to actually land astronauts at the South Pole. These missions have faced delays, but they are coming. And this is where we have to stop and address something that has been lurking under the surface of this entire story. The question that you might be asking right now. If we are going back to the moon for resources, for strategic positioning, because of competition with China, because launch costs have dropped, because we found water ice, then what took so long? Why did it take 54 years from Apollo 17 to Artemis 3? Why not 30 years? Why not 20? The honest answer is that all the things we have talked about had to happen first. The water ice had to be discovered and confirmed. The launch cost revolution had to happen. Private companies had to develop the capability to build rockets and spacecraft that NASA could not afford to build on its own. The geopolitical situation had to shift in a way that made space competition feel urgent again. All of these things took time to develop. None of them were inevitable. They were the result of individual decisions and technological breakthroughs and historical accidents that unfolded over decades. But there is one more piece of this story that we have not talked about yet, and it might be the most important one of all. It is the piece that explains not just why we waited so long, but why going back is so much harder than most people realize. Let's talk about what the moon actually does to human beings. Because for all the engineering challenges of getting there, the biological challenges of staying there are in some ways even more daunting. The moon has no global magnetic field and essentially no atmosphere. This means that the lunar surface is continuously bombarded by cosmic radiation and solar particle events. On Earth, our planet's magnetic field and atmosphere deflect and absorb most of this radiation. In low Earth orbit, the International Space Station is still inside the protective bubble of Earth's magnetic field, and astronauts there receive elevated radiation doses but manageable ones. On the Moon, you are outside that protection entirely. The radiation environment on the lunar surface is significantly more intense than in low Earth orbit. Long-duration stays on the Moon, the kind needed to actually establish a base and conduct meaningful scientific research, expose astronauts to radiation doses that increase their lifetime cancer risk substantially. Apollo astronauts were not exposed to dangerous doses because they were only on the surface for a few days at most. But living on the Moon for months, which is what a real base would require, is a different challenge entirely. There are solutions. Habitats can be built with radiation shielding. One of the most promising ideas is to build habitats inside existing lava tubes, enormous underground tunnels formed by ancient volcanic activity, where the rock overhead provides natural shielding. The lunar South Pole is also thought to have somewhat better radiation conditions than other parts of the Moon because of the geometry of the solar wind at high latitudes. But none of these solutions are simple, and none of them are cheap. Then there is lunar dust. This sounds almost trivial compared to radiation, but ask any Apollo astronaut and they will tell you that lunar dust was one of the most persistent and irritating problems of the entire program. Lunar regolith, the fine powder that covers the surface, is nothing like the dust you find on Earth. Terrestrial dust is rounded and smooth because it has been tumbled by wind and water for millions of years. Lunar dust has never been tumbled by anything. It sits in airless vacuum, exposed to micrometeorite impacts, and it gets charged by solar radiation. The result is particles that are sharp, jagged, electrostatically sticky, and extraordinarily fine. The dust got into everything on Apollo. It clogged equipment, it scratched visors, it abraded spacesuits. Harrison Schmitt, the only professional geologist to walk on the Moon, developed what he described as hay fever-like symptoms from lunar dust that accumulated inside the lunar module. There are genuine concerns that long-term exposure to lunar dust could cause serious lung damage, similar to silicosis, the lung disease caused by fine silica particles in miners. For a short surface stay lasting a few days, these are manageable inconveniences. For a permanent base, they are serious engineering and health challenges that require serious solutions. And then there is the Moon's extreme thermal environment. During the 2-week-long lunar day, surface temperatures in sunlit areas can exceed 120 degrees Celsius. During the equally long lunar night, temperatures can plunge to -170 degrees Celsius or lower. That is a swing of nearly 300 degrees between day and night. Equipment and habitats have to be designed to survive and operate through that entire range. None of this is insurmountable. Engineers are smart people, and these are engineering problems. But they illustrate why building a real presence on the Moon is genuinely, deeply hard in ways that go beyond just building a bigger rocket. Now let's zoom out even further. Because the return to the Moon is happening within a context that is broader than just NASA and SpaceX and China. There is an emerging commercial lunar economy that did not exist 10 years ago and barely existed 5 years ago. The discovery of water ice and other resources on the Moon has attracted the attention of investors and entrepreneurs in a way that would have seemed like fantasy during the space shuttle era. Companies are developing commercial lunar landers, mining concepts for extracting and processing lunar regolith, solar power systems optimized for the lunar environment, communication networks for the Moon. The ecosystem of companies involved in lunar activities has expanded dramatically. NASA itself has been deliberately trying to foster this commercial ecosystem through a program called the Commercial Lunar Payload Services Initiative, or CLEPS. Instead of developing government-owned lunar landers, NASA has been contracting with private companies to deliver scientific payloads to the Moon. The idea is to create a market for commercial lunar delivery that sustains itself independent of any single NASA mission. The early results have been mixed. Some of the commercial landers have run into serious problems. Astrobotic's Peregrine lander, launched in January 2024, suffered a propellant leak shortly after launch and never reached the Moon. Intuitive Machines' IM-1 lander, launched in February 2024, reached the lunar surface but tipped over on touchdown, leaving it at an angle that prevented some of its instruments from operating properly. But it landed. It communicated. It returned data. It was the first American spacecraft to land on the Moon since Apollo 17 in 1972. 52 years between American lunar landings. And these early failures are not surprising. Early spaceflight was full of failures. The first American orbital launches exploded on the pad regularly. The Mercury program had multiple crises before Glenn orbited Earth. The history of any new technology is a history of failures that teach you how to succeed. The commercial lunar industry is in its early adolescence. The failures are painful, but they are also how you learn. What is remarkable is not the failures but the pace at which the private sector is now moving. 5 years ago, a commercial company landing on the moon was a theoretical possibility. Today, it is a demonstrated capability, however imperfectly. 5 years from now, it will probably be routine. And this brings us to the most fascinating and in some ways the most important question of all. What does the return to the moon actually mean? Not in terms of flags and politics and prestige. What does it mean for the long arc of human civilization? Because I think we are at a genuine turning point, not a manufactured one, not a public relations narrative, a real one. The Apollo program happened in a world where space was a government activity, a thing that nations did with public money for national purposes. The technology of the era essentially required this. The cost of development was so high, the risk was so uncertain, and the timeline was so long that only governments with essentially unlimited budgets and political mandates could sustain the programs. That world is changing, not because governments have gotten less important in space, they are still enormously important, but because the cost of access to space has fallen far enough that private capital can now participate meaningfully. When the Falcon 9 can launch a payload to orbit for a fraction of the cost of the space shuttle, when Starship is designed to push costs even lower, the range of activities that make economic sense in space expands dramatically. This is the same transition that happened with computing. In the 1960s and 1970s, computers were room-sized machines that only governments and large corporations could afford. The miniaturization and cost reduction of computing technology over subsequent decades eventually made computation cheap enough for individuals to own personal computers, and then cheap enough for everyone to carry a supercomputer in their pocket. The social and economic consequences of that transition were enormous, in ways that nobody fully predicted. Something similar may be happening with access to space. Not on the same timeline, not in the same way, but with potentially comparable consequences. If launch costs continue to fall, if in situ resource utilization on the moon becomes practical, if a commercial economy in cislunar space, the region between the Earth and the moon, begins to develop, then the moon transitions from a place that humanity visits occasionally to a place that humanity occupies and exploits as an economic asset. Now, that transition is not certain. There are many ways it could fail to happen. The technology might not mature fast enough. The economics might not work out. Regulatory and legal frameworks for resource extraction on celestial bodies are still deeply uncertain. The Outer Space Treaty of 1967 prohibits national appropriation of the moon, but is ambiguous about whether private entities can extract and sell resources they find there. The United States passed a law in 2015 asserting that American companies can own resources they extract from space, but this is contested by other countries and not universally accepted under international law. But even acknowledging all of these uncertainties, the direction of travel seems clear. The moon is becoming a place rather than a destination, a location with ongoing human and robotic presence, with infrastructure, with economic activity, rather than a flag planted in empty silence. And here is the thing that I think gets lost in most of the coverage of the return to the moon. The 54 years were not wasted. They were not, as it might appear from a certain angle, simply a period of failure and stagnation. Yes, we did not go back to the moon. But during those 54 years, we learned things. We developed technologies, we made discoveries, we built capabilities, we created an institutional understanding of what it takes to sustain a human presence in space, through the Space Shuttle program, through the International Space Station, through robotic solar system exploration of extraordinary breadth and depth. We discovered water ice on the moon, which changes everything about what is possible there. We developed rockets that can land and be reused. We built a global community of space-capable nations where once there were only two. We created a private space industry that did not exist. We learned from the shuttle's failures what a sustainable architecture for human spaceflight needs to look like. None of this is to minimize the frustration of 54 years without a human moon landing. That frustration is legitimate. Decisions were made in the 1970s that set back human space exploration by decades. The shuttle program, despite its many achievements, was an enormously expensive detour. The cancellations of promising lunar programs under multiple administrations represent real lost opportunities. But the story of why we did not go back to the moon is also a story of why going back now might actually stick. Why this time, unlike every other time it was seriously proposed over the past 5 decades, there is something more than political will and government funding driving the effort. There are resources driving it. There is geopolitical competition driving it. There is a commercial ecosystem driving it. There are dramatically lower launch costs enabling it. And there is a fundamentally different architecture underlying it, one built on the explicit goal of sustainability rather than the implicit assumption that everything would be figured out once the flags were planted. Whether Artemis and the broader vision it represents will succeed is genuinely unknown. The history of ambitious space programs is littered with grand visions that ran out of money and political support. What is different this time? The commercial involvement, the international competition, the resource imperative might be enough to sustain momentum through the inevitable setbacks and delays, or it might not. But the 54 years, that long, strange gap between Apollo 17 and whatever comes next, that gap was not just failure, it was also accumulation. The accumulation of knowledge and technology and capability and economic reality that makes what comes next possible in a way that it simply was not before. There is one more thing worth saying, because amidst all the policy analysis and engineering challenges and geopolitical competition, there is something at the heart of this story that goes beyond all of that. Something about what it means to be a species that looks up and decides to go. When Neil Armstrong stepped off that ladder in 1969, he said it was one small step for a man, one giant leap for mankind. He was right. It was genuinely one of the most remarkable things our species has ever done. And for the 12 people who walked on the moon during Apollo, the experience of standing on the surface of another world and looking back at the small, fragile, brilliant blue sphere hanging in black space was transformative in ways that are hard to articulate. Every single one of them came back changed. Some of them became environmentalists, struck by the fragility of that thin blue atmosphere visible from space. Some of them became deeply spiritual, overwhelmed by the sense of perspective that looking at the Earth from 250,000 miles away provides. Some of them became advocates for peace, seeing for the first time from that distance just how arbitrary the lines we draw between countries really are. The moon is close enough to visit in a few days, far enough away to look back and see the whole Earth at once. It is a natural place from which to gain perspective, and perspective is something that our species, wrapped up in the day-to-day noise of politics and economics and conflict, perpetually needs more of. The people who will walk on the moon in the coming years, whenever it happens, will be the first human beings to stand on that surface in over half a century. They will stand in the shadow of mountains that have not been touched by sunlight in billions of years. They will look down at water ice that fell from comets that formed in the earliest moments of the solar system. They will look up at Earth and see, as those 12 men before them saw, just how small and precious and lonely it really is out there. And maybe, in some small way that is genuinely impossible to quantify, that matters. Not for the resources, not for the strategic positioning, not for the national prestige, but for the simple, ancient, irreducibly human impulse to go, to see, to understand, to be somewhere no one has ever been before. That impulse did not disappear during the 54 years. It was waiting. It was building. And everything that has happened since Apollo 17, all the frustration and the detours and the failed programs and the budget fights and the engineering disasters and the slow accumulation of new knowledge, all of it has been, in a sense, the runway for what comes next. The moon is waiting. It has been waiting for 4.5 billion years. Another few years will not matter to it at all. But to us, to the species that first walked there in 1969 and is now, finally, genuinely, making plans to go back, those years mean everything. We did not wait 54 years because we